Hi, this is Nick from Facebook. In this work, we're going to show you how we're going to do encoding parameters prediction for convex cell video encoding. In 2018, convex cell video encoding was proposed to provide the optimal selection of resolution in QP for adaptive bitrate streaming. Suppose we want to deliver m different lanes in an ABR streaming ladder. Convex cell video encoding takes a video and split it into shots. Encode each shot with m resolution and n QPs. We then combine it through dynamic optimizer by matching the constant quality bitrate slope to obtain the optimal resolution and QP for each shot. In this green table here, you can see a target quality 92. Shot 1 might use 1080p, but shot K might use 720p. This is optimal, but this is n times the complexity compared to the conventional encoding scheme. So in our prior work, a faster encoder is used to perform the analysis encoding step. This can significantly speed up the analysis process with the small loss in BD rate compared to the full convex cell encoding. So each shot will be encoded using a faster encoder at m resolution and QPs. And through dynamic optimizer, we can then obtain the encoding parameters, which are selected using this faster encoder. This parameter would be then taken to a slower encoder with a better compression efficiency. So the limitation of this approach is this can only apply to encoders in the same coding standard or standards with a similar quantization scheme, such as VP9 to AV1, but not H.264 to VP9. And second is, the faster the analysis encoder, such as a hardware encoder, the more loss in BD rate will be observed. In this work, we present two different approaches to address the limitations. First, we want to be able to predict encoding parameters within the same coding standards. So here, we train a machine learning model between a fast encoder and slow encoder, so that we can predict what the bitrate and distortion of a slower encoder would be from the bitrate and distortion of a faster encoder in the same standard. So we take a video, we go through the faster encoder, we got the bitrate and distortion. Then, by machine learning model, we predict what will be the bitrate and distortion. And the rest is the same. We can obtain the encoding parameters from the predicted bitrate and quality. In the second approach, we want to be able to predict encoding parameters across different coding standards. To do this, a cross-codec QP map is built to map the optimal encoding parameters from one codec to another. This will save time needed for the analysis step even more significantly, since the earlier generation will be orders of magnitude faster than the later generations. For example, we can take a video and use H.264 encoder for the convex cell encoding analysis step. And then we put it through the cross-codec QP mapping and obtain the predicted encoding parameters, which would then use for a encoder from a later generation, such as VP9. And the map can be built in a way by encode a variety of shots with M resolution and QP. And by finding the closest average quality between codec, we can build such map. These are the experiment results. So first we'll look at the prediction within the same coding standard, where we use a hardware H.264 as an analysis encoder and software X.264 as a slow encoder. So these are the BD rate compared to X.264 very slow with fixed CRF. So present the original convex cell encoding, the one we use faster encoder as analysis, and also with the predictive modeling. So as you can see, by predicting the bitrate and distortion, we can improve the BD rate performance and gain back majority of the loss from using a fast encoder for analysis. And the other set of results where we predict across a coding standard, where we use X.264 very fast as the analysis and libVPX as a slow encoder. And the table shows the BD rate compared to libVPX CPU 0 with fixed CQ level 38. So as you can see, with cross-codec prediction, only 11% more CPU time is needed for analysis to achieve a massive 20 to 40% BD rate improvement over conventional fixed QP encoding. The takeaway is, the original convex hull encoding can provide 20 to 40% BD rate gain over conventional fixed QP encoding, but at a much higher complexity. In our prior work, we use a faster encoder. It can be used to speed up the analysis step at some loss in BD rate. And here we present two approaches. One is we can predict the modeling. We can bring back the majority of the loss from using a faster encoder. And also we presented it is possible to predict across codecs, and this can further speed up the analysis by using an encoder from an earlier generation coding standards. With that, thank you for listening.